So you can say rate of heat transfer without insulation, or rate of heat transfer something is wrong here. Insulation equal to 1/4 of without insulation. I don't know why it's not picking insulation without insulation. So that means what about the resistance? Okay, we can talk about the resistance. Here we have only one resistance. What is that? RH. RH. Okay, convection resistance. So the temperature of the surface here is T2, and the air temperature is 32. Okay, and between that there is only convective resistance. When it comes to the insulated pipe, we have two resistances. One is the conduction resistance RK. The next is the convection resistance RH. But the temperature difference here is remains same because we have given this temperature outside the pipe that will remain same. It is mentioned in the problem, and this is outside air temperature that is also will remain same. Okay, so what is the thing here is if you write the rate of heat transfer for with insulation, then I have to write two. Okay, resistances, that is T2 minus TA divided by RH plus RK plus RH. Okay, RK plus RH, and then that should be equal to 1/4 of. If you T2 by RH. Yeah, T2, that temperature difference is same, T2 minus TA divided by only RH. Okay, but this RH is calculated with respect to radius R1. Okay, R1 is the outside radius I'll take. So that is R1 equal to 17.5 millimeter. Whereas, okay, sorry, that is I think R2 only. In the problem it's mentioned R2. So let's take this is R2 and this is R3. So this is R2 with respect to R2 and this is with respect to R3. So that's the only difference. Okay. Now you can from this equation you can write RK thermal conduction resistance plus the convection resistance at R3 equal to 4 times convection resistance at R2. So right, R2 is known to us, that is 17.5 millimeter. Okay. Now we have an equation. If you substitute for RK, you know this is a cylindrical wall. So RK is nothing but ln R3 by R2 divided by 2 pi length. We will take unit length. Okay. Or if you keep it also, no problem because it will cancel out. L, then we have thermal conductivity A plus what is the convective resistance? 1 by H A. Okay. What is the area here? Now R3 is the radius. So area is 2 pi R3.
2 pi RL.
2 pi RL. R3 is the radius of after insulation. Then H. HA. And what about right hand side? We have 4 times. What is this? Again, 1 by 2 pi R2. Now R2 L into HA. So you can see that 2 pi L is common everywhere. You can take it out.
So in the first term, you have cancelled the R2, R3 in the denominator.
Which one?
So isn't it 2 pi LK R2, R3?
Sir, there won't be R, right?
No, 1 minute. Which one you were talking? 2 pi?
So first term, 2 pi LK R2, R3.
No, that is spherical wall.
Okay, okay.
Cylindrical it will not go. Okay, spherical it will be 4 pi L K R1 R2. Okay, so R3 will remain here. Here R2 will remain. Okay, so leave it as it is, and now I can write multiply by K everywhere. You can write ln R3 over R2. If you multiply by K, then you have K by HK into 1 by R3, 1 divided by R3, and this is 4K divided by HK into 1 by R2. So you have the equation with only one unknown, that is R3. Okay, you can check it. So what is K by HK, you tell me? And substitute that here. ln, this can be written as ln R3 minus ln R2. So I will take it to the right hand side. Plus, what is K? 0.0. Thermal conductivity 0.07, and H is 10. So K is 0.07 and H is 10. So K by H will be 0.007. K by H is 0.007. 0.007 divided by 1 over R3. And right inside, you simplify. Tell me what is we get. You have 4 times 0.027, 1 by R, sorry, 0.0175. Okay.
Sir, it should be ln R3 by R2, right?
Which one? ln? Yeah, that I will bring here now. Okay, that's what I told you. Okay. So that one I will put here. ln R2. ln R2 will come here. So 17 point. Okay, 0.017. Okay, so right inside everything is known. You can just calculate and tell me. K by H equal to 0.007. Okay, that is meters if you want. So this is actually what is, can you tell me what is K by H actually means?
So critical radius.
Critical radius. You can see that outer radius of the pipe is more than critical radius. So there is no question of critical radius in this case, okay, because it's less than the inner radius there. Okay. So Simplify, and what is this value right inside? How much it will be?
Minus 2.445.
This is minus
2.4.
2.44.
44. Yes, sir.
Yeah. So substitute now, and okay. How we solve it? That is now question, right? How we can solve this? So you can write this as R3 multiplied by R3, then ln R3. So give this OneNote is giving a lot of trouble for me. 2.44 R3 plus 0.007. Is it correct? Because I'm multiplying entire equation by R3 and I'm writing this equation, which is a transcendental equation. Transcendental.
So do
Because
we
that-
need to write the equation in this form, or can we directly solve using the calculator?
You can solve using calculator, but this equation has to be written first. Okay. Only
Okay,
after
sir.
writing this equation, you should write the solution. Because it's an iterative solution, you can write iterative solve like method R3 is equal to minus 0.007 plus R3 ln R3 writing so badly. R3 divided by 2.44. 2.44. Okay, so now on the left hand side we have the same unknown. On the right hand side also we have same unknown. So we can say this is the new value and this is the old value. And you start with the old value, some guess value, because we know inner radius R2 we know. So R3 should be more than that. Okay, R3 should be more than R2. You start with some value. Say, let me start with 0.05 meter. That is 50 millimeter I took. Okay, you can start with 20 millimeter also. So only number of iterations will be more. So this is my sorry, not R2. This is R3. R3 0 first guess value. This is called guess. Now what you do is substitute this R30 here and obtain the new value. Then substitute that one into this equation. You will get another value like this, and finally you will get a converged solution. Okay. So tell me what you get converged solution. Or if you want, you can tell me the new value first. If you use R30 or old value as 0.005, what is the next value you will get? Yeah. Yeah, do it. So anybody is not following, just tell me. Okay. Only thing
So
is,
why are we taking these new and old values? Why aren't we just solving that equation that we got, that transcendental equation?
how you solve it? Tell me.
Using the calculator, I got the value of R3 as 283.
How much? How much you got?
283.
283.
No,
Something
sir.
is wrong with that. Okay. So something is wrong with your value. So the correct value should be 79.3 or 436 millimeter. Okay, correct value 79.3 79.365 millimeter.
79.8 mm, sir.
Okay, 79 point some. No, if you do it further, it will increase to that value. Okay, but I stopped at this one. Okay, check it. So this you can obtain in different methods also. You can adopt Newton-Raphson method. Newton-Raphson method you have studied, right? In mathematics.
Yes, sir.
Yeah. So that is the formula you can write. Okay. R3 nu equal to R3 old minus f of R3 divided by f dash R3. Because this is a polynomial transcendental equation which is a function of R3. You can write this as function of R3. Okay. And you have to write the find the derivative of this function in order to use Newton-Raphson method. So you substitute these are for the old values. If you use Newton-Raphson, you will get the solution in 3 iterations, just 3 iterations. But you have to calculate these values separately and substitute. Okay. Okay.
Sir, so we got this value of 79.365. Now, what are we trying to find out?
So that's all. That's the radius of insulation, but you have to give the thickness, determine the thickness of insulation.
So that's just R3 minus R2, right?
Yeah, exactly. That is
so I didn't understand the old and new that you have written.
Oh, this is a transcendental equation. You cannot write explicit equation for R3. Can you solve? Okay. Can you solve this equation? For example, if you have a some equation where, for example, if you don't have this log function, can you solve that equation?
Yes, sir.
Okay. Yeah, very easily, right? You can take out R3 and that will simplify to some numerical value. But you cannot simply solve this equation. How can you solve this equation? Maybe
so even for this equation, if we put it in the calculator, we can get the value. I got the value of 79.84.
How you got it?
Sir, there is an input to put in a formula and it just solves for the variable x.
Okay, that's what you're depending on the calculator for everything without knowing how it does. That's the thing, right? Nachiketa.
Yes, sir.
Okay, yeah. But what I am telling you is how it does the calculation. Okay.
Okay.
So you try with this one. You take the guess value of this some value. That doesn't make any problem. Okay. Only number of iterations will be different. You can take 20 millimeter, but it should be more than 17.5 millimeter. Why? You know that. Okay, that's the diameter of the
R2,
radius of the pipe. Okay, R2 is already there. So it should be more than that. So select some value and substitute here. Okay, if you know how to program your calculator, instead of using directly the equation from the calculator, you can also program it. Okay. So just write this right hand side and you can use this as the answer or some other variable and give that variable name and keep on calculating. Okay. Yes. So anyway, your calculator will also do this only, iterative method only. There's no other way. Okay. Because it's a non-linear equation.
Yes, sir. So we don't need to show this in the exam then, right?
So of course, I don't insist on showing the iterations, okay? But you have to write this equation. What I underline here, that equation must be there. Final equation. Okay? Yes.
Yes. Excuse me, sir.
Yeah.
Sir, I didn't get the. I mean, I didn't get 79.365. I got 58 mm. How? I have to do more
So
than
just
one
take-
iteration.
How many iterations you did?
How many are we supposed to do, sir? I mean, minimum number
Okay.
of.
So you just keep on doing that iterations. So previous value, you tell me, you got 58, right? After one iteration. That's correct. Okay.
Yes, sir.
So after one iteration, you'll get some 58 millimeter or 0.058. And you do next one, it will be somewhere 62 or 63 millimeter. Okay. And you have to repeat it. It may take 20 iterations to get this value. Check it. Okay. That's what you have to write the program in your calculator. Simply.
Okay, sir. So
Yeah,
when the values start coming the same, like the old and new value become same.
It will not change it at all. So that means it's converged. Okay.
Okay, sir.
Yes. Okay. Another similar problem is there. That is, you can do it. I'll tell you anyway. An electrical wire of 5 millimeter outside diameter. So the wire radius R1 is 5 by 2 or 2.5 millimeter. And the rubber of thermal conductivity. So this value actually I have changed here, but usually rubber material, it has a thermal conductivity of 0.16. But if I take 0.16 for this radius, then the thickness of insulation is very large. Okay, critical thickness. So that's why I have changed here to K value of 0.042. Okay.
So here critical radius should be less than no, like the thickness should be less than.
This is actually insulation only. This is insulation.
No, since this is an electrical pipe.
Electrical wire, okay.
Yeah,
Right.
RO should be less than RC, right? To allow
R1, yeah, R1 should be less than RC. Yes. So what is RC for this value of you can calculate. Okay. What is RC? K by H. So what is K by H here? K is 0.042 divided by H value is given as 12. Tell me.
3.5 to the
3.5 millimeter. Okay. 3 point. This is reasonable. But if you take K value of 0.16, you will get very large value. Okay. That thickness of insulation itself is maybe 10 millimeter or more. So it's not reasonable. So that's why I changed the value. Okay. So then, yeah, what is the question here is not to find the critical thickness, but find the thickness of rubber insulation, which keeps the heat transfer same as it was a bare wire. That means we have to find out, okay, the same problem, similar to the previous problem. Okay. Rate of heat transfer with wire, with insulation. So let me just write once. Something is wrong with the OneNote or the MS Teams. I cannot write over here. Rate of heat transfer. Give me 1 minute, okay? Let's try. Now it is okay. So heat transfer with insulation. No, we have same problem here. Insulation. So I'm writing something and it is appearing something else here. So shall I do without? Shit. So it's, what is the problem? Okay, so again the problem is similar. Here what is the is rate of heat transfer with insulation is same as without insulation. That's the condition. Find the thickness of the rubber insulation. Okay, which keeps heat transfer rate same as the bare wire. Okay, so that you write with insulation is you have two resistances. So you can say that RK plus RH at radius R2 now is same as RH so in the previous problem it was 4 times, but here now it's RH at R1. So nothing else, same. Okay, so we have written a relationship here, but here it is 4 times, but there it is only same as the bare wire. So you can do it, I think. Okay. Okay. Question number 19. Calculate the admissible current intensity for a 2 millimeter diameter copper wire.
Sir, could you tell the solution of the previous question?
Which one?
Previous question. What's the solution?
Yeah. Solution. Okay. So maybe 5.14. So check it. Okay. I will. R2 will be 5.14 millimeter. Okay. So what do we have here is calculate the admissible current intensity for a 2 millimeter diameter copper wire. 2 millimeter diameter. So D1 or R1 is 1 millimeter. Covered with insulation of optimum thickness. Now, what does that mean? Optimum thickness?
RC.
Yeah. So
RC,
thickness of insulation is so I had to give up because I cannot write like this. Some strange thing is happening today with OneNote. So, I'm not sure whether it is because of internet.
So type.
There is RC minus R1. Maybe because of internet or some issue here.
So maybe you could try writing in Paint.
Paint or yeah, maybe I will try with that. Okay, so we have wire of radius R1 and the critical thickness of insulation for given K value. K value is given as 0.015 watt per meter degree centigrade, and H value 10 watt per meter squared degree centigrade. So you can calculate RC value, that is K by H. What is the value? What is the critical radius?
1.5 millimeter.
Yeah, how much is this?
So 1.5 millimeter.
Yeah, 1.5 millimeter, right? 1.5 millimeter. Okay, so R1 is 1 millimeter. So R2 is, that is equal to R2. R2 equal to 1.5 millimeter. Thickness of the insulation?
So 0.5 millimeter.
Yeah, 0.5 millimeter. Now you have to do the calculations for the rate of heat transfer. Okay, so rate of heat transfer through the this thickness of the insulation. What is the condition here? So so that to have a positive heat transfer, positive means so heat loss should be there. That should be maximum here because of optimum thickness. On the condition that maximum temperature of insulation should not exceed 60 degrees. Now, when you have an insulation over a wire, so where you expect the maximum temperature? So this is the insulation.
Inner side.
Yeah. So on the surface of the wire, we have the maximum temperature.
So your voice is not very clear.
1 minute. So temperature is highest. Is it okay?
Yes,
Still?
sir.
Okay. So T1 is maximum, or the surface temperature of the wire is the maximum, and that should not be more than 60 degree because the insulation temperature cannot exceed 60 degree. Should be less than or equal to 60 degree. But outside air temperature and H value is given. Air temperature TA is given as 30 degrees centigrade. Okay. So we can calculate now what is the heat transfer through the insulation. So rate of heat transfer through the insulation, rate of so how we can write here, because we have two resistances. One resistance is for the thickness and other is the convection resistance, RK here and RH. So the temperature here is 60 degree maximum value, and here is the atmospheric temperature PA 30 degree. So write Q equal to T1 minus TA divided by RK plus RH. Substitute for okay. We can write here for unit length of the wire. Unit length of wire. Because we are length of the wire is not given, so we will take a 1 meter length of the wire. So substitute, that is 60, or you write the formula for RK and RH, that is ln R2 by R1 divided by 2 pi K. L I am removing because it's 1, and here it is 1 by 2 pi R2 HA. Okay, substitute. So Q equal to 60 minus 30. Otherwise, separately you can calculate RK and RH values. Okay, and substitute here. ln 1.5 divided by 1 divided by 2 pi K is equal to 0.015. That is RK plus RH 1 divided by 2 pi R2, that is 1.5 into 10 power minus 3 into HA, that is 10. Be careful here. Why I do not write here 1.5 into 10 power minus 3? Because it's a ratio. Okay, R3 minus R3 by R2. No, R2 by R3. Okay, so 10 power minus 3 will cancel out. But when you write here radius for this case, you have to write that substitute in terms of meters. Okay. So tell me, what is the rate of heat transfer? How many watts?
So 2.
2 point. Okay.
2.01, sir.
2.01 watts. Okay. So then we have to find out now what is the current through the wire which produces this much heat energy. Okay, because this is the steady state heat transfer that will limit the temperature to 60 degree. Okay, so then how to calculate that? The wire current intensity through the wire.
I square R.
Yeah, I squared R. So we know the resistance of the wire per meter is given. The resistance of the wire per meter is given. So it's very easily, we know that since we are taking 1 meter length of the wire, so resistance R is known, and the rate of heat generated should be 2.01 watts. So equate it and find out the current intensity.
So what's the value of R?
Okay. So resistance. Electrical resistance of here. Right. Electrical resistance of wire of 1 meter length wire. 0.005 ohms. Okay, so rate of heat generated Q equal to V into I or I squared R. So we know this is should not be more than 2.01 watts. Okay, so we can solve it for I, that is 2.01 divided by 0.05. Take the root. So how many amps? 20.05
20.05.
amps. Okay. So this is the maximum current intensity that is possible through the wire. So next we pick up another problem. Here again, one more thing is sometimes the resistivity of the wire can be given instead of the problem states here the electrical resistance of the copper wire is given. Okay, so instead of that resistivity rho will be given, then you should know how to calculate resistance. Rho L by A. Resistance equal to rho L by A. So next question is for heat transfer through a varying cross section. Varying cross section. Okay, we have a Frustromov.
Sir, can you take the previous one?
Yeah. Okay.
I just need to
This
copy
one,
the
right?
last.
Yeah. Okay. This one or previous one?
Yeah, this one only. Thank you.
Okay.
Done, sir.
Okay. So truncated cone of 300 millimeter height, okay, constructed of aluminium. The diameter of the top is 75 millimeter, bottom is 125 millimeter. Lower surface is maintained at 95 degrees centigrade, upper surface is at 540 degrees centigrade. The outer surfaces are okay, well insulated. Assuming one-dimensional heat flow, what is the rate of heat transfer? Given K aluminium is 205 watt per degree centigrade. So what we have is a truncated cone.
So
Yeah.
I think we could assume this as an elliptical cross section.
Yeah, any cross section can be asked. Okay, elliptical cross section or the cross section can be a square, right? The problem can be changed, but here it is cone. Okay, truncated cone. So that you have the diameter of the bottom that is given as 125 millimeter. Top it is 75 millimeter, and the length of the cone is given as 300 millimeter. Okay, height is 300 millimeter. So you can see the figure, right? Clearly.
Yes, sir.
Yeah. So what we have to do here is just go for fundamental law of heat conduction. Okay, Fourier law of heat conduction, and apply it to a element. Then integrate it from x equal to 0 to x equal to L. Or so this is say the direction. We fix the coordinate x on the top. Okay, let's select a so I'll select a element of thickness delta x. Okay, thickness delta x. Okay. So what we have to do now is to write the radius or the area change for this element of thickness dx. Now this element is at distance x from the top. So what is the radius at that location? That we have to write the equation for that. So let me say radius r1 is the top radius here. So that is the radius here. What is the value? Diameter is 0.075 meter. So radius will be 0.0375. And bottom here, the radius R2, that is 0.0625. Okay. So in between, anywhere, if you want the radius, how do you calculate? That should be between R1 and R2. Okay. So how do you calculate the radius at this point? This radius here, R.
Sir, R equal to 0.0375 plus.
Yeah, R1 plus
R2 minus R1
R2 minus, yeah, R2 minus R1 divided by, let me say this is the length, okay, length of the cone, given as E is misleading here, okay, length of the cone, L into X, okay, into X. So depending on the X value, okay, if X is 0, then we have R1. If X equal to L, that is the R2 value. Okay. So this formula, this factor, we can substitute as some other okay, notation S I will use, where S equal to, we know what is the value of S now, R2 minus R1 by L. Substitute these values and you can calculate and tell me that value. Okay.
0.0833.
0.083. 860. Repeat. Can you repeat, please? 0.08. 33. Okay, so no, this is a ratio, so there's no unit. Okay. So we can write now simply this equation for radius. Now area of heat transfer also required for us. What is the area of heat transfer? Area of heat conduction at any x. Okay, what is that area?
So pi r square.
Pi r square. Okay, pi r square. So you can write r square is nothing but r1 plus sx. So pi R1 plus Sx whole square. Now apply the Fourier law of heat conduction and solve it. Okay. Applying so what you can write Q equal to minus Ka GT dx. So we have area is given as pi R1 S into X whole square. Okay, that is equal to minus K, area is now pi into R1 plus S X whole square into dt dx. Integrate from where to where? R1 to R2. For X, you have to integrate from R1 to R2. So you can write Q into dx.
So 1 to R2 or across the length?
Oh, sorry, not R1, R2. It's from 0 to length. Okay, yeah, right. Yeah, 0 to L. So X divided by R1 plus Sx. This has to be integrated from 0 to L. And the other side, we have minus K into pi dt. And this has to be integrated from temperature limits, that is T1 to T2. T1 to okay. So can you integrate this? I'll transfer same equation to the next slide. Select. Okay. So integrate this 0 to L. So integrate Q into this is to the power raised to the power 1 integration R1 plus Sx raised to the power minus 1 dx. So everything is lost. No recoveries. So everything is gone, right? Okay. So we have to
Sir, what's the answer?
yeah, okay, 1 minute. Whatever I was doing, that is gone now. I have to repeat from there. Okay, Q 0 to L, and we have R1 plus S x dx. On the right hand side, we have minus K into pi integral T1 to T2 dt.
For R1
And
plus S to the power
yeah, to the
minus
power
1.
minus one, right? Raised to the power minus 1. So this will become minus 1 into R1 plus Sx to the power minus 2 into S. Okay, so we are integrating with respect to x. So apply the limits 0 to L, and on the right hand side we know this will be K into pi into T2 minus T1. Okay, so substitute for the S is okay, minus sign here.
So the original
Yeah.
equation was Q integral dx by rs r1 plus sx square, right?
Yes, sir. It's
Oh,
not
it was
the integral.
square, right? Oh, sorry. It's not raised to the power 1. Area squared, r squared. So yes, minus 2 it is. Okay, let me change here itself. Minus 2. So what will happen here? We have 2 minus 2.
So minus 1 r plus sx raised to the
Sir,
power minus
plus
1.
1, sir.
Minus 2. Or you will
Integrating it.
yeah,
Sir, we are integrating, sir.
integrating. So this is minus 1 into. This is minus 2 here. So plus 1, right? So this will be minus 1. So then this is 1 by minus 1. So it anyway it's like so we have
That is 1 by S. 1 by S. Oh, never mind.
it's correct, right? So something wrong? No. So we have okay, S is known to us. What is the S value? We can substitute here. R1 is known. Everything minus S. Then you substitute the R1 plus S. Oh. This divided by R1 plus Sx. Something is wrong, right? I am multiplying here, so it should be division, not. So then, when you integrate this one, it should be minus 1 by S into R1 plus Sx. Okay, this is correct one. Apply the limits 0 to L. Okay. So we have to divide by S. Yeah,
So
S has to. Yes, because when you differentiate, s will come, so that has to be cancelled. So s has to be divided. You can check it. The cross checking is to find the derivative of this one, and you should get exactly this. Check it. Okay. So if you take the derivative, you have minus y 1 by s. This, and if you take the derivative of this one, you will have r1 plus s x to the power minus 2 into s. So this s, sorry, minus s. So this s will cancel. This minus sign will go. So you have this. Okay. So today's class, I think, had a lot of problems with this OneNote. So I had to see what is wrong with that. Yeah, substitute the limits. Okay, you have upper limit L. So you can write Q. Okay, since it's minus sign here, so I'll substitute the lower limit first. So you can write this as S, because this is 0, S into R. S can be taken outside, and you can write this as 1 by R1. Okay, when you substitute L, what do you get? Minus R1.
R1, R2.
Yes, yes. No, that is 1 by R1. When I substitute the lower limit, it is 1 by R1. Then when I substitute the upper limit, it will be 1 by R1 in plus SL. And on the right hand side, I can write this as K pi T1 minus T2. Simplify this one with a taking common denominator here, R1 into R1 plus SL. So you can write this as Q by S R1 into R1 plus SL. So this will give you R1 plus SL minus R1. Okay. So then simplify this one. What do you get? R1 will cancel out. And
So 128.01 Q.
1 minus T2. So you can simply substitute for R1 and SL, okay, and you will get the Q value. What is the value? What?
2238.14.
223.
So
Yeah, but we can simplify this one. We can simplify this one further, and by substituting the S value. Okay. So what do you get?
2.2 kilowatts, sir. 2.23 kilowatts.
Not 223.
No, sir. 2238.
Something is wrong with it. Okay. Anyway, I think I will stop today because I'm trying so many things, but not working. So let's extend next week, next class, okay, for 15 minutes so that I can cover this. So I'll not keep on trying this again. So anyway, okay. So Monday we'll continue, okay?
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you,
Okay,
sir.
welcome.